Okay. Okay. All right. So that should be recording. Um, Hello, everybody. I hope your like past 2 weeks was good. And I hope everybody got a chance to like take a look at the chapters. So I did. I read through chapter 1 and I just like followed along in like Python. I didn't actually like do anything because there's like I don't know. He just like leaps into stuff and I was just like, whatever. Um, Chapter 2 and 3 were like kind of interesting. There was like the ethics section, which was like kind of cool. But it like, yeah, I don't know. It was nice to read like a good like ethics section. But I didn't really have like a lot of stuff to reflect on. Chapter 4 was like where things like actually got fun. So I could like, I read it and then I got excited and then I just like leaped into making a digit classifier. Like I didn't actually do the 3s and 7s thing. I just did the full 10. Which I think is actually a mistake. I think like it was better learning to do the 3s and 7s separately. So I don't know. I figure what we do is just like walk through kind of what we did or talk about questions or anything like that. So if people don't mind, I will go first and just kind of show people like my little Pluto notebook. Okay, so I hope people can see that. I'll make it a little bigger. So like basically what I did here is I started writing like a notebook with the intention that it would be like so that you could read, and then like I got halfway through and I just forgot to finish it. So it's we just it's varying quality. But basically I just do all the imports. I got to play around with like trying to make my GPU work, which was actually really fun. And it's actually so extremely easy to do in Julia. Load the MNIST data set, get like a first example. There's a really nice package called Gray. They're called Colors. Is it Colors? Yes, I think it's Colors. That gives you this Gray function that converts like a two-dimensional array of 0 to 255 values, and you can convert it into the representation of the image. So I was using this for like demos. And apparently this is a 5, which honestly, this tells me a lot about the downfall of America. If you can't write a better 5, like, come on, this is just garbage. Yeah, this is what it is inside of the data. I made a nice little processing function because processing the data is like a pain in the ass because like you want to get all the x things and the y things. You want to reshape it so that it's a vector and not an array because Flux doesn't like natively handle like n tensors. And then I rescaled it to be between 0 and 1. By just dividing by 255, but I don't actually know if anybody, because I remember doing it without this step and it was like kind of fine, like it did okay even if you didn't do the rescaling. So I'm sure people have comments on that. Did anybody do it without rescaling, and like was it fine for you? Yeah. Okay. Oh, somebody put up on the chat. Okay. Ideally, you always want to scale to keep the gradient small. Okay, yeah, that's a good point. All right, thank you for that, Nikos. And Dominic did not rescale, but it was okay for this example. Yeah, I imagine this gets really, really hairy when you start having a lot more inputs and things like that. I also have this thing like automatically construct a little validation set for me and wrap it inside of a data loader. Because having I just needed a validation sample or validation set. And if you use Flux training.jl as like a way to do like auto training, which I implemented to begin with, and then I walked back and did the basic version. It's nice to have like a validation set in a data loader. This is how you send all of your data to the GPU. If you haven't done this, you just do like GPU and you pass it in. And if you haven't seen this little symbol here, this is a pipe symbol, which is just the same as it is in R. Like you take all of this stuff and put it in the first argument of this thing. I think I ended up using a batch size of 512, but my GPU has like kind of enough memory that I could go like a little higher. I think I did 2056 as a trial, but batch size, very important for making things go fast. Oh my God. And feel free to jump in with comments as I go through this, because I also want to have other people show us kind of what they did. So I get valid load and train load, and these two things are just data loaders that contain either the validation set or the training set. And then I made a cool little like Pluto thing where you can actually like type in the number of layers you want. You can type in how thick it is, right? So this is like each layer, they're all homogeneous, so it could be like five units thick or 10 units thick or whatever. And the way this is implemented is just a little markdown thing. So I just inside of here, you interpolate with the dollar sign says like, hey, execute this code first and then stick it in there. And then I just give it a number field thing. This stuff is all inside of Pluto UI. And then you can set like the training epochs and stuff like that. So this is the way that the model is actually constructed. So I was just using CellU, but it works pretty well with ReLU and other stuff. So I should also add like a little drop down for some activation functions too. But for this problem, like any activation problem function just seemed kind of fine, like they just all kind of worked. So yeah, this is a very small model and ends up being very, very small. So 8,000-ish parameters. Or a little accuracy function. Nothing super interesting in there. This is setting up the optimizer. I use a learning rate of 0.001, 1e-3. But you can play with this and it's like a little sensitive. I think if I went above this, like if I went above 0.001 to like 1e-2 or something, it ended up being like pretty bad. Or at least very slow to start looking like it was converging. And then here's my little training loop. All I do is I go through each epoch, I use the add progress thing so that I get this little progress bar here because I fucking love progress bar. And then you go through each 500 batch sized feature and label. And then you take the gradient and then you calculate the cross entropy. And then grads is, I don't remember what the first value is. I think the first value is like the actual loss function. And then you update with the gradients. And then I'm also saving the training accuracy and the validation accuracy so that I can use them right here inside of this plot. And this is the, this is our little validation and accuracy, or validation set and training accuracy plot. This one's actually pretty bad. I got this up to like 99% or something in both train and validation if you make it like pretty deep. But I'm sure as we get along to like CNNs and stuff, that'll be slightly better. That's how this gets plotted. Then I have a little prediction thing. And then I added like a little slider. So like what you can do here is you could just kind of, here I have to zoom out a little more. You can just kind of scratch through the examples and it'll tell you what probability the model thinks the number is. I don't know that probabilities are actually appropriate here, but this is like the model's like confidence level. So this is to me, this is a 9. But the model, because this is not a very deep model, is like, this is a 3 with almost certainty. So, but I thought I would play with this inside of the test set. So that's all the stuff I've got there. So I don't know if people like want to walk through kind of what they did and whether they have questions or thoughts or anything like that. Anybody? Bueller.
Thanks for sharing. I didn't actually get through to the examples, but I just wanted to join and see what actually went on. But yeah, thanks for sharing the what you put through.
Yeah, absolutely. I think I put this up on the website too, so I think it's so yeah, I think we can link to it too. I haven't put it in the book. Patrick said he's sick. He has a fever, so he's not going to join today.
Oh shit. Okay.
He's been like up all night, I guess. But so the book, I'll write the intro, and I think Patrick's thing is actually really nice. So I may go through that after other people go. All right. Who else has like even like scratch work where they were like, I did like this stuff?
I also just read through the chapters. You have to work on them. Yes.
Okay. All right. That sounds good. We can also have, we should also have people like go through the little chapter that Patrick wrote, because he also did a very good version of this. All right. See if I actually also I can send out the link to the thing. I think it's in. All right, I'm going to stick this in the chat. So this is the link to my little Pluto script, which you should just be able to run as like a normal script inside of your in your computer, but it has like a bunch of package stuff that you need to handle. Okay. Unless somebody wants to show us some of their stuff, I also want to walk through like what Patrick wrote. Because Patrick has actually. Okay, I hope you can see this chapter that he threw together. So I think I still want to add some writing to this because I think we can. I think it's just kind of nice. I'll sit down and do a little more writing in this. But he does a very simple job of like outlining how you actually call the gradients, get the gradients of things. Do people understand how like autodiff worked in Julia? Was this like a thing that made sense to people? Like how to call the gradient and get stuff like that. All right, cool. Doobity. Dude, Linux is free if you don't value your time. Holy shit. Okay. And he ends up doing this cool little visualization of gradient descent, which is just like kind of awesome. Like I think this showcases the extent to which Dominic was able to get it to work with pretty well in Julia. Honestly, that's one of the things that I still really like about Julia. It's like how easy the autodiff system is. But yeah, we'll get into it a little bit. One of the nice things about Flux too is like working in Flux, which is so kind of regimented. It's actually, you know, the autodiff is actually really nice. Like I work a lot in like Turing, for example, where like you have to be super careful about the types. Like if you write a function that like only works with float 64 as an input, for example, autodiff changes, or most types of autodiff change the underlying type of the variable. And so like rather than float 64, it's like a forward diff dot dual. And so then the function doesn't exist as far as Julia is concerned because it only knows how to accept a float 64 input. So Flux doesn't actually have this problem, which has been really nice, where it just kind of like works with whatever the type is because you're mostly just working with matrices. But anyway, so people got how gradient descent works. Like, was this like a, you know, the gist here is like, for people who are not familiar with gradient descent, you have like a curve, you take the gradient at this point, which is like a line that goes like this, and then you like scoot slowly down the curve until you get to the bottom point here. But if you make this learning rate too big, you can actually make your problem much worse. So it actually doesn't really pay to have like a massive learning rate. And I think, am I wrong that Jeremy had a few things with like how to like heuristically determine what the learning rate was? Does anyone remember that? I feel like we discussed this, but I don't remember. It was like something about the validation set, like the relative accuracy or loss or something. Anyway, Nico says that okay. All right, you don't remember that. Okay, that's okay. Maybe that was in a later chapter. I think I like accidentally went ahead. I was like very excited and I kept reading. So now chapters like 4 through 6 just blend together for me. Struggled with the intuition for learning rates. Okay, that's actually a good note. A scheduler. What's a scheduler?
Hey, I might be using the wrong term, but something where your learning rate decreases as you progress through the training. So you initially have a high one to approach the solution, and then kind of what's the word? Kind of anneal it as you need it to be smaller.
Yeah. Okay. Cool. Wait. What was that? What's the command for this in Flux?
Yeah, Flux had Flux accepted a type of learning rate that was based on, I think the command was exponential decay or exp decay, and that had a type of scheduler, and Flux accepted that as a learning rate, which was very helpful.
Oh, okay, that's cool. All right, I like that. Okay, well, cool. I learned something. That was great. Thank you. Okay, learning rate finder in later chapters. Okay, all right, cool. So it did blend together. All right, so the scheduler is kind of cool. So I'll look into this. So I think this is like flux.gl. Okay. Oh, okay. So you changed the learning rate over some other optimizer. Okay, that's cool. I ended up using Atom, which I think is like slightly more complicated because I think it has a momentum term, but this looks great. Okay, cool. Thank you. All right, cool. I learned something today. All right. Do you want to talk about the learning rate intuition, or is that like are you like good now?
I might be curious if anyone else had any solutions for finding their learning rates. It was very much trial and error for me.
You know, I think I also did learning like trial and error. Like I think it was like, especially for a problem like this that's really fast. I think it's like you know, pretty easy to do trial and error. I don't know how you would do this in really big cases. Like, you know, if you're training like a 70 billion parameter model, like presumably that takes like a long ass time. And like, you don't want to run this thing like 15 times to try to get a good learning rate. So I suspect there's actually some just like really good papers about how to like heuristically ex ante determine learning rates. But I know that he does have some interesting stuff about how to determine it in the next chapter on pet recognition. Anyway, anybody else have comments about like choosing learning rates or intelligent ways to choose learning rates? Okay, cool. So Patrick ended up doing like actually a very intelligent way of unwrapping everything. Usually run a test problem for multiple learning rates. Okay, so you'd have like, so you'd like batch into like smaller data sets. You'd do like, you know, like a 10, like 1%, 5%, 10%, something like that. And then you would run it for multiple learning rates. Is that right? And plot the accuracy with respect to learning rates chosen. Oh, okay. All right. That sounds reasonable to me. Okay. Yeah, Nikos has some good descriptions there in the chat. That actually sounds pretty reasonable to me. Okay, yeah, I still need to watch Andre Karpathy's videos, because he like, I've seen like a little bit of stuff, but he's so good, like, oh my god. Okay. I wasn't aware of this mosaic function. That's actually really great. I love this, where you just like make this little MNIST mosaic, which is really nice. One hot batch was very useful here. I don't know if people were able to do this. Do people understand why we're using one hot in coding?
I don't know
Like,
there was a
oh,
function.
go ahead. Yeah, there's a very lovely function for doing this kind of thing. There's one hot, which is just for encoding like one observation, and then there's one hot batch, which is for encoding like k observation, which actually works really well. So he did a great job with just like general data cleaning and stuff. All right. And then what is he doing here? Okay, so this part here is just making the training set and the validation set using split ops, which I think somebody actually recommended in the chat, which is really nice. I ended up forgetting to use that, but that's a good way to split your observations. And he's using a validation size of 30%, which I think is another heuristic thing. I think like 20% is like common, 30% is common. I would actually be interested in knowing a little more about the math of choosing like different learning rates. Like, do you really want to like, or different validation set sizes? Sorry, it's 7 in the morning for me, so I'm like a little frazzled. But yeah, I would love to know a little more about how you choose your validation set. Like if there's properties of the data that you have in mind that are like, well, you actually need a larger validation set here because it's like lower variance or higher variance or more bias or less bias. I don't know. He wraps things in a data loader, which I think is roughly equivalent to what's the name of the thing in Python? Unless you make some assumptions about noise level or differentiability, you can't really make statements about validation set. Yeah, I guess that makes sense to me too. Like the problem with all of these like big neural network things is like, when I come at them from like being an econometrician, when you work in like kind of classical statistics, like there's a lot of like actually pretty general rules about things, and like a big like language for describing the theoretical nature of how you make estimators and how you estimate stuff. And just like one of the things I've just been like so impressed with and kind of like shocked by when I'm looking at like deep learning stuff is like how little that language exists for deep learning, because like these things are so hard to describe. They're like extremely non-convex functions. They're like just hideous. Like you kind of have to describe them in terms of like what they do after you fit them. And that's like really weird to me, like we threw everything out of the window. Exactly. Right. Like the whole thing is just like, you just pick a learning rate, like, and one of the things I love too is like, because the neural networks are always super non-convex, like they're hard to estimate, hard to optimize. We just like decided that it doesn't matter whether or not you hit a global optima. Like you're just like, okay, I'm just gonna fit it. Because like you have no guarantees about getting an optimum. Especially if you're doing like gradient descent stuff. Chat approach, exactly. Like deep learning is like chat statistics. You're just like, I don't know. Let's just fit it with whatever. Also, anyone can jump in at any point. Don't let me talk too much. If you're like, oh, I want to say a thing, just start talking, and I'll shut up. Okay. So this is like a pretty like simple representation of the model. I have like actually a pretty deep model. Patrick here goes for 784 on the outside, on the input side, because you need one for every pixel, and then 32 as the hidden layer size. You know, I played around with this a little bit. Like, one of the things that I think I'm really interested in with like neural network architecture is how much the relative like depth versus like thickness influences like how effective your model is. So I was able to get like, you know, obviously they're both kind of increasing. So if you like make it thicker or you make it deeper, it seemed like it had better accuracy, which I think makes perfect sense to me, because it kind of minimizes your like, or lowers your makes it more flexible. Oh, we got a good rule of thumb here in the chat. What's the good rule of thumb?
I will intervene vocally because I'm too lazy to type.
Perfect.
So basically, if you read any state-of-the-art paper with LLMs and the graph neural networks, you'll see that most of the times all the MLPs are just two-layer MLPs.
Really?
And that's it. Two layers, 128 neurons, and that's it. And it works.
This is very interesting to me because, like, you know, my like general sense is that if you're doing like an NLP thing, you know, the deeper you make it, the more it's able to pick up on like just weird stuff inside of your data, right? It generates all these weird features inside.
Yeah. Well, yeah. If you think about a single MLP, sure. But if we're talking in the context of transformers or graph neural networks, you have a lot of quote unquote MLPs, and each single of these component will be a two hidden MLP.
That's really cool.
Yes, they're deep, yes, in that sense, or in the context of graph neural networks, you have the same MLP acting n times, but it is just a two hidden layer network.
That's really interesting.
Ideally, you want to make them as shallow as you can, because the deeper they are, the more expensive it is. So
right, but the performance, like, so the performance is not more, doesn't outweigh the additional cost, at least not currently.
Yes.
Okay. All right. All right. That's a great little comment. Thank you for adding that. That's so great color. All right, I'm making a little note for myself. Any see any DeepMind paper on GNNs. Okay. Man, that was solid. That was a solid rec. Yeah, we got some smart people in here. I love it. Okay, so we got a nice shallow layer here, which is a good thing. He also ended up using Atom because Atom was actually pretty good, I guess. Wasn't there like some issue with like AdaGrad or Atom or something like that turned up in a paper like several years ago? I feel like I'm half remembering this. I wasn't really following the space at the time, but people were like upset with one of the optimizers. I don't know if anyone remembers that. Yeah. Anyway, so he does loss functions and accuracy after fact. He makes like a nice little dictionary to store results in, and then he does the training label, which is more or less the exact same thing that I had, that they put everywhere inside of Flux, which we can get rid of in future versions. Like we can just use Flux training just because like we don't need to make this custom thing every time. Okay, Nikos has a thing in here. Mesh representations.
Well, don't read it right now, but
yeah,
I mean, just for reference.
Sorry, it's like I was like, oh man, I gotta read this right now. Thank you. That was
put it in the bookmark cave.
Yes. Okay. Exactly, the list of things we don't ever read. Okay, and then he basically gets training accuracy, etc. This is all kind of additional stuff. and he has a little plot that generates your accuracy and loss over time between the training and validation set. So this thing actually here I thought was interesting, right? This is like a thing that I kind of like look out for a little bit, is like when you're the loss in your validation set starts to go up. This is like an overfitting thing, right? That's like the sense of this, the heuristic I have is like when the validation set starts to diverge in the loss, it's an overfitting thing. I don't know if people have that sense as well. It's happening a little bit too with the accuracy. The accuracy starts pulling apart. Oh yeah, Pluto is terrible for real programming. It's like a little clunky. Well, it's not terrible, but it's just like it can be a little clunky. So I agree, especially with neural nets. Like that was one of the big things where I was like, okay, each one of these takes like kind of a long time to train. And so like anytime you change something in Pluto, if it's like somewhere up on the DAG where like, you know, variable X influences the following things. Vim gives me PTSD. Vim is great. Although I started using Helix recently, which is like a Vim like a slightly better, it's like a, you know, it's like a Vim light kind of thing with some extra bells and whistles. And it's really nice. It's good. We know. Okay, so I think that's about what he has here. And there's this other stuff in here. Did anyone do the mean, like the classifier based on just the mean of the cells? Did anyone do that?
Yeah, I did
not.
basically everything from the chapter, but the mean one was pretty short.
Oh, okay.
I can share that screen.
Yeah, sure.
Yeah, I mean, I just did it in Juno, so I don't have like a fun notebook. But
That's totally fine, man. I don't think I'm gonna make a notebook for the future ones. I think I'm just gonna write a script.
Can you guys see that?
Yeah.
Yep. Okay. Let me drag all the Zoom stuff out of the way.
Yeah, it's been a while since I've seen Juno.
Yeah, it's like not being updated anymore, right?
Yeah, it's dead. This is once Microsoft bought GitHub, the whole Atom thing just kind of died.
Yeah, I think I started using it right before that happened, and I'm kind
Me
of
too.
using it right until they like someone physically deletes it from my computer.
Yeah, well, the plus side, VS Code is actually really good successor to Atom. I've not been mad. They've made VS Code really good.
Okay. Makes me more likely to switch. But okay, here's my mean implementation, load the data, stack the arrays. I mean, the mean super easy to take, and then here's that whole chunk for the distance classifier. But I haven't started Julia, so let me start that and I can run all this. Yeah, not much to it.
Yeah, okay. All right. I dig it. That's great. Anybody else have anything they want to share, or something they found to be like interesting or novel, or something that they thought was hard?
From the lessons, right?
Yeah. Well, it doesn't also have to be from the lessons. If it was like something you tinkered with, or if it's Julia code, like anything like that.
Okay, so the past weekend, I had in my backlog to build an ML library from scratch because I've been using machine learning for about 5 years. Okay. And I want to get into the nitty-gritty. So I had in the to-do list to build everything from scratch for a long time now. I did it this weekend.
Ooh.
The fun part is that my implementation of the quote-unquote library, but don't call it a library, is about 10 to 15 times on CPU versus Flux, which means that Flux is very unoptimized for CPUs. they're not doing Julia stuff properly.
Yeah, I think I agree. I think the CPU stuff has like fallen off a little bit because like they were focused on like the GPU side, because I think that's the biggest margin.
On the other hand, on GPUs, it's almost impossible to do with Julia kernel fusion right now. Like we have the CUDA kernels, fusing them, all the operations in one kernel is what PyTorch and JAX are doing, and Keras, of course, are doing in the backend. Julia cannot do that. So this results into about 10 to 20 times slower GPU code.
Yeah.
Which is a problem.
Yeah. Wait. So why can't it do kernel fusion?
Oh boy. Because you'll have to somehow. Okay, technically you could do it in Julia, but it's a very, very demanding project. Like it took the JAX team a couple of years to do it with Google Mining. We have something similar kind of coming, like Enzyme.
Yeah.
But this is still very, very experimental. But for the moment we have.
Oh, sorry, go ahead.
No. For the moment, Flux is not very good on CPU, but it is what we have right now. Like, okay.
Yeah. Yeah, I think another thing here is like Lux.jl, like architecturally has a lot of promises that they can do, like make things better as well. Like one of the things that's like that I think a lot of people do in Julia that ends up like not being very productive is like making things mutable. Like, you know, one of the big claims of working with Lux is that it's going to like make everything pure functions, and having pure functions is great for compilers, and like they're just like, oh, okay, I know exactly what's happening here. I don't have to touch IO or modify anything. I just input output.
This is great on GPU programming where memory allocations don't matter.
Yeah.
Lux right now is about, in all benchmarks I've run, about 20% slower, but it has a cleaner API. That's true.
Yeah.
The API is cleaner, but there are no performance boosts by using Lux at the moment.
Yeah. I don't think there's going to be any for a little bit, but I think that because it's just hard to make things performant, especially like if it's like a 20% gap. You know, that's a slow gap to close. But the advantage of having things be immutable and stuff is that I imagine it's probably going to make a lot of the raw CUDA stuff like a lot easier to do, just because like CUDA is like pretty fragile. Like it you know, you need everything to be like just so, and having like a pure kind of immutable framework that's built around that on the Julia side makes it a lot easier to like, you know, talk to the CUDA kernels in a way where they're like, oh, or talk to CUDA in a way where it's like, oh, okay, cool. You know, we don't need to like go crazy here. I'm giving you an input. Here's the output. It'll be nice. But you're right that it is slower.
I dumped the GitHub rep of the quote unquote project.
Okay.
Which has some benchmarks and some gradient tests and some benchmarks versus Flux. And one can see what I did to make it go faster than Flux. Okay. Basically abusing loop vectorization. There's this library called Simple Chains that is extremely fast on CPUs. It is made by the SciML community, Chris Rakakakas and the rest of the gang. They're using all sorts of tricks and pushing the Julia compiler to the extreme to get the performance they're doing, because right now, Simple Chains is faster than JAX on CPU, which is very, very impressive.
Yeah. Okay. So this is actually super incredible. Okay. So the chains function is what Nikos is talking about here. You know, in Julia, we had this, like when we were specifying the model structure architecture, we were using this chain thing here. But Simple Chains is like more or less seems to be the same kind of API, right?
it is similar, but besides some simple testing, right now I do not recommend simple chains. They
Oh, why
still
not?
have a lot of rough edges. I was about to get I don't want to say the fact, a bad word, but I tried to use simple chains for a commercial project at my company, and some very obscure simple chains bug almost got me ruined.
Okay.
So I am biased on that. I am biased. So simple chains is not thread safe. So if you do any parallel computation with simple chains, you will have bugs.
Yeah.
If you pass an unjoined of a matrix inside a simple chains model, it will spit results. There will be no warning of an error. Everything will look perfect, but the result is gibberish. Why? No one knows. No one knows.
Okay, well, that's not great.
This is the price of freedom. Okay, this is great. Stuff not working is great because there is no other way to go forward.
Yeah, I think that I suspect that the way that SciML people actually use simple chains is that it's like very internal. Like it's very like they're able to structure it very heavily because they're like working with differential equations or whatever. Because it's Chris, right? If it's Chris is involved, it's like it's a differential equations thing for sure.
Yes.
That dude loves differential equations. I like imagine all of the stuff that you're good at in your life. Like maybe you're like a good friend and like maybe you're like pretty good at certain types of math and like maybe you can paint. Like take all of those things that you're good at and take all of the points that you allocated to being good at those things and put them in differential equations and you get Chris. That dude loves that stuff. Which is great for us because now we get all this cool differential equation stuff. Okay, but yeah, simple chains. Yeah, okay, definitely avoid it, but I think that's like kind of a promising thing. There's lots of very cool, promising things in Julia, which I like. Although I would like some things to be as fast as they're supposed to be. Okay. Okay, cool. Well, I'm glad you're working on like a fun little project. That's always great. I love a new project.
I mean, the project was complete, and I will be using this for production right now instead of Flux.
Okay.
An X10 performance boost is always welcome.
Yeah. Anybody?
So far, I've been using Flux in production for my startup. We have some AI models that we're deploying through Flux.
What kind of are they, like vision things or language things or?
They are, you guessed it, differential equations.
Of course it is.
Basically, what we're solving is weather routing optimization for marine vessels.
Sure.
We write the whole thing as a loss function that we back propagate through. And we're using Flux and AutoGrad to find the parameters of the model that minimize the fuel consumption, of the differentiable fuel consumption. Can you see where this goes?
Yeah.
Differential engineering.
Yeah, that's very cool.
So yeah, we used to use JAX, but we opted out for Flux just for it, no specific reason. And now some AI models that are included in the loss function now will be this ML library you're seeing.
Dude, that's cool. That's great. All right, awesome. Well, I'm happy to hear that. That's really neat. Dude, shit, that's great. Okay, so we have like, I don't know, a few minutes left. If people want to like, does anybody else want to share like stuff they've done or like questions they had or anything interesting? Okay. So I think for the coming week, we're going to do the next chapter, which I think is it chapter 5? Yeah, chapter 5. And what is chapter 5? Chapter 5 is on pet breeds. Here, I'll share this one here. So this is just like going to be a nice little image classification thing. So I think we're working with it. Is it ResNet? Yeah. Okay. So we're going to work with ResNet. And as like a little tip for this, I think, is it Metalhead? Has a bunch of computer vision stuff. So they have like pre-trained values. So they have ResNet here. So you should be able to load stuff from Metalhead to get access to the pre-trained models. So we don't have to do the like training stuff by ourselves. We can do the fine tuning and stuff. But this will be the, oh no. Yeah, okay, ResNet is pre-trained here. So thankfully we don't have to do that. But I imagine we could maybe do that on our desktops. I don't know, or whatever resources we have access to. I'm not sure. Who knows? Okay, questions about that? I guess we can do this next week or the 2 weeks. I don't know how people felt about the 1 week versus 2 week cadence. Okay, cool. Well, let's chat about it on the Discord. I'm sure we'll probably end up doing it next week. Or something, depending on where people are. All right, cool. That's all I got. Anybody else got anything? All right, party. Thanks for hanging out, everybody. I appreciate it. We got some cool stuff so far. Everybody have a lovely day, and I'll start posting code and stuff for my next thing. And I hope you guys do the same.
Yeah.
Thanks,
definitely.
Aria. You have a good day or evening.
Yeah, you too. Evening. Yeah. Bye.
Bye-bye.